Yeah, I can see that, Alex.
Okay, so let's just start. So I'm going to be talking about connecting three manifold triangulations with monotonic sequences of elementary moves. And well, maybe I should start by saying I have a lot of slides, and I'm not expecting to get through all of them. So my plan is just to sort of take this slowly, and we'll just see how far we get. That also means if you have a question, then like feel free to ask, and if it takes time to answer it, it doesn't matter because I don't care how far we get. Yeah, so I guess I should start off by telling you like what all this means and why we care about it. Hopefully I don't really need to introduce this, but I think it's good just to make sure we're on the same page with definitions. So three manifold is a topological space that kind of locally looks like ordinary three-dimensional Euclidean space. And I guess, I don't know, these are interesting objects and we want to understand them through algorithms and through computation. And for that, we need some kind of discrete and finite way to represent three manifolds. So that's why we have triangulations. So a lot of people probably are used to simplicial complexes where, I mean, it's the same idea. You kind of glue tetrahedra together to build up your three manifold. But what I'm going to do is like my triangulations are going to be generalized in the sense that we allow two faces from the same tetrahedron to be identified. So these don't have to be simplicial complexes. It's basically, I mean, it's a generalization of a simplicial complex where you sort of allow more flexibility. And the reason we sort of want this is we can get more efficient triangulation. So this is a fact that I'm just going to black box, that every three manifold can be represented by a one vertex triangulation. So that means somehow like all the vertices of your tetrahedron, when you glue them together, those gluings cause all the vertices to be identified into a single vertex. So you have one single vertex in your entire triangulation. And these sorts of triangulations tend to be also quite efficient in terms of the number of tetrahedra as well. So this is good for computation, as we'll see shortly. So the thing is with triangulations, right, is if you fix a three manifold, you can have many different triangulations of that single three manifold. And I guess somehow in theory, it doesn't matter which triangulation you use to compute with. And so for practical computation reasons, you want to pick like a good triangulation. So it's sort of interesting, at least, like because there's so many triangulations, you want to know like how are all these triangulations of the manifold related to each other. And I guess the natural way to talk about this is, talk about local moves to retriangulate. So here's kind of the really classical notion of 2-3 and 3-2 moves. So the idea is if you have anywhere in your triangulation, you just look at a small region where you've got two tetrahedra joined together, you can replace that small region with a little gadget that looks like this. So what this is you've got like this common edge in the middle and sort of three tetrahedra glued together along that edge. And what that gives you is it's really the same. It's just a retriangulation of this small region. If you do this inside a small region of like a bigger triangulation, then you get a new triangulation of the same manifold. And so you can keep applying these moves. So you can keep applying these 2-3 moves or the inverse 3-2 moves, and you get lots and lots of new triangulations of the same three manifold. You can talk about this as kind of this is just a useful way to kind of encapsulate all these moves and the structure of all these moves. So you build like this infinite graph where you take your vertices to be one vertex triangulations of your manifold with at least two tetrahedra. And we need at least two tetrahedra, right? Because to apply a 2-3 or 3-2 move, you need at least two tetrahedra. So we just ignore one tetrahedron triangulations. So as I say, this gives you an infinite graph. And you can naturally arrange the vertices of this graph in levels. So you have all the two tetrahedron triangulations, all the three tetrahedron, all the four tetrahedron, and so on and so on. And okay, what are the edges of this graph? You connect two vertices if they're related by a 2-3 move. So for example, if I put this edge in here, what this is saying is that this triangulation, if you perform a 2-3 move on it, you get to this triangulation. Or equivalently, if I perform a 3-2 move on it, I can get back to this triangulation. And you can, okay, so you can fill in all these things, and you make an infinite graph, locally finite but infinite graph. And the theorem, which goes back to, I mean, it's, I guess in the scale of things, it's not old, but this is, I mean, it's okay. So it's Studematvev and Pigolini, and basically, it's if I give you any three manifold, maybe I should say closed three manifold. There are more general versions of this theorem, but let's say closed three manifold. Then its pachnograph, this graph that I've told you about, it's actually connected. So you can get between any two triangulations of your three manifold via 2-3 and 3-2 moves. And this is sort of the launching point for what I want to talk about. Yeah, so as I said, like, we want to have good triangulations. This is sort of motivation. We want to have good triangulations for computation purposes. And often what that means is you want to have a small number of tetrahedra. I mean, this maybe seems natural, but let me actually give you an explicit example of where this is really important. There's these things called normal surfaces, which is useful for computation. But you can do things like recognize the unknot or recognize the three sphere with these surfaces. And the way these surfaces work is you embed the surface in your triangulation so that each time it intersects a tetrahedron, it's either in one of these triangles, or it's a collection of triangles and quadrilaterals. So the intersection of your surface with each tetrahedron is a collection of triangles and quadrilaterals of the form that is shown here. And sort of the important thing with normal surfaces is, like, you have these three quadrilateral, sort of three types of quadrilateral. And because you want your surface to be embedded, you can't have sort of two quadrilaterals of different types in a tetrahedron. So, like, for example, if you look at this quadrilateral here, it's sort of, if you were to cut the tetrahedron along that quadrilateral, it sort of splits into two halves, right? And if you look at the other two quadrilaterals, like this one, for example, it goes from one half of the tetrahedron to the other half. So there's no way to put this quadrilateral and this quadrilateral in the same tetrahedron without having a self-intersection in your surface, right? So then your surface wouldn't be embedded. So because your surface to be embedded, if you're sort of trying to determine the existence of a normal surface, you always have to check this embeddedness condition. So you have to sort of choose which quadrilateral type that you have in each tetrahedron. So if you have n tetrahedra, right, and there's three choices of quadrilateral, or you can choose no quadrilaterals. So that's sort of four choices in each tetrahedron, which is like 4 to the n things that you have to, 4 to the n possibilities, because you have to do this for every tetrahedron. So you've got this exponential factor in the running time of your algorithm, right? You got this 4 to the n, and like that means you want this n, the number of tetrahedra, to be as small as possible to keep your computations practical. Okay, so here's sort of the application is, because you know that you can connect things with 2-3 and 3-2 moves, you can just kind of try to walk through the pachnograph to try to find a triangulation. It's useful to have other moves. So I say possibly other moves, because if you have another move that works, then why not use it for practical purposes? And we now have like really good heuristics for doing this. So, like, for example, Regina has like routines that are often very effective at retriangulating with fewer tetrahedra. I just wanted to mention very quickly some work in progress that I'm sort of, I mean, this is pretty fresh, which is, I mean, there are other measures of complexity for triangulations. So like, we don't have to, like, somehow up to this point, whenever people talk about simplifying triangulations, they almost always mean we want to reduce the number of tetrahedra, but that's not always the most important measure of how complex a triangulation is. So for normal surfaces, like what you really care about is number of tetrahedra, but for other applications, there are other measures of complexity that are more important, and maybe we can sort of try the same strategy. You walk through the pachnograph, you perform local moves to try to retriangulate, but instead of reducing number of tetrahedra, you reduce some other measure of complexity. For example, for people, if anyone happens to know, for example, you can reduce the tree width. You try to reduce the tree width of a triangulation using local moves. But that's sort of very fresh and work in progress, and I won't say anything about that because there's not so much to say about it yet. Okay, so here's sort of a question, which is, like, we know the graph is connected, but we don't know a whole lot more about how sort of well connected it is. Like, do you have, if I give you two triangulations, does there exist a short path? Does there exist sort of many options for what path you choose between them, for example? So, like why even ask this question? Like, I guess I've already mentioned this first reason, which is that it's often surprisingly effective in practice to just walk through the pachnograph searching for example, a triangulation with fewer tetrahedra, which suggests that the pachnograph is well connected, right? If you can always, like, in practice, we can always find this short path somehow. And so that suggests that somehow it's not just connected, it's somehow well connected. And so we want to explain that. And number two is sort of related, which is, if you can prove that the pachnograph is well connected in some way, then maybe that's something you can exploit, right? Maybe you can actually use that to get to like a better method of exploring the pachnograph, right? So it's all kind of coming back to this idea of, we care about this because it could be useful, right? Okay, so what do we currently know? And I sort of already said this, which is not a whole lot. Despite our kind of practical experience that tells us the pachnograph is well connected, actually proving things about it has turned out to be like pretty hard. So in terms of like lengths of sequences, there's probably, like, this is probably about 20 years old. So Mijatovic showed for large classes of three manifolds that you can get tower of exponential upper bounds on the length of a sequence of 2-3 and 3-2 moves, which, I mean, that's terrible. Like, these grow incredibly fast. And practical experience, again, so I keep coming back to this, practical experience suggests that these bounds are far from time. Like, there's no way these are the actual correct or optimal bounds, at least intuitively. But this is the best we have at this point, which is in some way a bit distressing. But anyway, so there's another result, which is from a few years back due to Henry Segerman, which basically says, if you ignore triangulations with degree 1 edges, so you actually throw away some triangulations, which is like deleting some vertices of the pachnograph. The triangulations that we throw away are the ones with degree 1 edges. So what that looks like is a degree. Okay, so what is a degree 1 edge? What does that mean? It means an edge that only meets exactly one tetrahedron in your triangulation. So what that looks like is you have this edge here that's sort of connected to those two blue triangles, and you kind of fold those two blue triangles together. And that kind of, this edge now is kind of internal to that entire kind of tetrahedron. So it's only going to meet that one tetrahedron. So that's what a degree on edge is. And so if we throw away all the triangulations that have these degree 1 edges, which means you're deleting some vertices in the pachnograph remains connected. So you can delete some vertices and it's still connected, which is sort of getting at this kind of, the pachnograph is somehow well connected. Yeah, I mean, this is kind of, why do I mention this? It's partly because this is it's quite a weak restriction on the pachnograph. And somehow we should be able to prove more than this intuitively, but again, this is proven quite hard and no one's been able to do it. So this is somehow more or less what we know about connectedness of the pachygraph, like more or less what we know I already mentioned, which is, as I say, maybe a bit distressing. Okay, so what have I looked at in terms of trying to attack this problem? So this is a fairly natural thing to ask about, which is monotonic sequences, which I guess when people think of monotonic, really what you would love to have is, if I want to simplify a triangulation, you want to have a monotonic sequence of moves. So every stage your moves only decrease the number of tetrahedra, because that would be super easy, right? Then you just, to simplify a triangulation, all you have to do is at every stage keep decreasing the number of tetrahedra until you can't anymore. And we know that's not always possible. Like there are local minima that are where like the only options are to go upwards in the pachygraph, but if you sort of go upwards far enough, you can eventually come back down. We know that's possible. There are lots and lots of examples of local minima. So kind of the next best thing then is, okay, what about you insist that the sequence breaks up into two parts? You kind of monotonically increase the number of tetrahedra until you get to some point, and then monotonically decrease. That's kind of the next best thing. Can you always find that sort of sequence in the pachygraph? So this is a question that I guess lots of people have worked on, and I've worked on, and disclaimer, I have not solved this. So I mean, here's the conjecture, which is what I just said. So this is the same statement as before, like the black part of the statement is the same as before, but instead of an arbitrary sequence of 2, 3, and 3, 2 moves, what I've got in red is this monotonic sequence. So you go up by 2, 3 moves and down by 3, 2 moves. There's sort of I mean, maybe it's worth actually saying heuristically, why you should believe this is true. Well, okay, maybe you should believe is too strong. Why it's reasonable to believe that this is true. So one thing you can think about is, if I give you two triangulations, this is like two vertices of the pachygraph, you can start sort of constructing a tree that goes upwards, where you just perform all possible 2, 3 moves. Right? You just keep performing all possible sequences of 2, 3 moves, which kind of builds like a upward. It's not a tree, but you can think of it as a tree, like a tree that's sort of subtree that's going up through the pachygraph, starting from one of your triangulations, and another subtree that's starting from the other triangulation, going up to the pachygraph. And somehow, if this conjecture were false, it would be possible that you have these two subtrees, these infinite subtrees that are going upwards, and they never meet. And that would just be really weird, right? Like somehow, I don't know, it's not a proof by any means, but it's kind of intuitively, these trees should meet at some point eventually. I don't know. That's heuristically maybe why you should believe this is true. Okay, but so what have I done? What have I done is basically you can prove this by using other moves. And the way this actually happened was, I was trying to prove this conjecture, and the result that I'm about to tell you about kind of just, it fell out of attempts to prove this conjecture. So here's some other moves that can be useful. So what you do is, now you're sort of not starting with tetrahedra, like you're starting with two adjacent triangles, which is why there's a 0 here, right? It's like the 2, 3 move, you start with 2 tetrahedra and turn them into 3. Here I'm sort of starting with 0 tetrahedra and puffing it up into 2. So that's exactly what I'm doing. You have these two triangles, and you kind of, you can think of the two triangles as like flat, and it's like not inflated. It's like a balloon, like a square balloon that's not inflated, and you kind of inflate up, right? And then you fill that space with 2 tetrahedra. So that's what a 0, 2 move does. And then the 2, 0 move, of course, is the inverse move. So you have this sort of configuration of 2 tetrahedra, and you sort of flatten it. I should mention that the 2, 0 move like you need some conditions to be satisfied for the 2-0 move to preserve the underlying topological space. For example, like if these two edges, like those two edges that kind of go around, if those two edges are actually distinct edges, then one of the things that happens is like you sort of squash those edges together, which is fine because like they sort of bound a disk, and if you flatten it, if you squash a disk down to an edge inside a manifold, topologically that doesn't into the manifold. But if those edges are identified, if those edges are glued together, let's say they're glued together such that this kind of region that's between those two edges actually forms an embedded sphere in your manifold, and you flatten that down to a point, then you're starting to change the topology, and you don't want that to happen. So there are some mild combinatorial conditions that you can impose on this to ensure that the 2-0 move preserves the underlying topological space, which, I mean, they're just kind of things like you don't want the edge to be glued to the other edge, that sort of thing. Anyway, right, so this is the first proof that I'm going to show you, which is right. So here's the fact that I want to very quickly prove because it would be relevant very shortly, which is a 3-2 move can always be realized by a 2-3 move followed by a 2-0 move. So what that means is, if I can get from triangulation A to triangulation B via 3-2 move, I could have done the same thing by doing a 2-3 move to triangulation A and then doing a 2-0 move, and I still get to triangulation B. And the way this works, the proof is just pictorial. So like the first triangulation here, this is sort of triangulation A, and you can do a 3-2 move, and that gives you triangulation B, right? And I claim that you can do this by 2-3 followed by a 2-0. And the way this works is, okay, so the 2-3 move looks like this. To convince you that this is a 2-3 move, so look at what happens up here. You've got these two adjacent tetrahedra. And if you just look at the edges, what happens to the edges? What you get is you have the same edges here, but you kind of have a new sort of diagonal that goes across, right? You introduce this new edge that goes through. And that's what I've done here is, okay, so you have this triangle here, and you sort of punch a new edge through that triangle, right? So what's happening here is you've got this blue triangle at the back, right? And I punch a new edge through that triangle, and that's sort of the 2-3 move. And like it's sort of maybe useful to actually visualize where the 3 new tetrahedra are in this picture. It's sort of probably I can't help much by explaining it, so maybe I'll just let people stare at it for a while and try to see where the 3 new tetrahedra are. But I promise this is a 2-3 move. Anyway, the point is, having done this, what you get is this configuration that looks exactly like what we have on the right-hand side of a 2-0 move. So we can squash that flat down into just two triangles. And when you do that, you just get left with these 2 tetrahedra here. Again, you should stare at this for a while and convince yourself. Yeah, maybe this is something like, if people want to come back to this picture, we can come back to it at the end. Anyway, this is, I mean, somehow this fact is going to be relevant for us. So remember that a 3-2 move can be replaced by a 2-3 move followed by a 2-0 move. Okay, so one thing you can do with this is sort of like an obvious corollary, is you get a corollary of the Matvei-Pigolini result, which is like, if you just replace every single 3-2 move with a 2-3 and a 2-0, then your sequence becomes a sequence that uses only 2-3 and 2, right? Which, as a corollary of Matvei-Pigolini, you can just get a sequence that uses only 2-3 and 2-0 moves. This is not interesting, but it kind of puts some context on this sort of theorem that's now, it's probably now roughly a year old, but I've been I mean, yeah. Anyway, so it's, I don't know, it's fairly recent. But the context of this theorem is it's kind of, we had that monotonicity conjecture before. That was like monotonic. There's like a monotonic version of the Matveyev-Piccolini theorem. And this theorem is kind of, it's a monotonic version of this corollary. So what I'm saying is between any two triangulations of the same three manifold, each with at least two tetrahedra, you can find a sequence that consists of an ascent via, so you go upwards via 2, 3 moves, and then you come down via 2, 0 moves only. So this is kind of quite restrictive. So again, this is somehow telling you that there's some kind of nice well-connectedness of triangulations. This does actually tell you something about the pattern graph, because you can also transform 2, 0 moves into 2, 3 and 3, 2 moves. So you could convert these 2, 0 moves into 2, 3 and 3, 2 moves if you wanted. And that would tell you something about the pattern graph. But I think this is the nicest way to state it, because you only, I mean, it's a very rigid structure with these moves. So how going for time? Okay, good. So I have like 10, 15 minutes to see how much of the proof I can get through.
We started 5 past, so you can go for another 20 minutes.
Well, okay. This is good, because normally I get to this point and there's like 2 minutes left or something, right? And I never get to say anything about the proof, or never get to say much about the proof. So this is good. I mean, okay, so I'm going to go through the easy part of the proof first. And this is the part of the proof that I've talked about a lot. So maybe people have seen this before, but we'll be able to do more today. So, okay, so you have some sequence of 2, 3 and 3, 2 moves, because Matveyev and Piccolini tell you that. And the idea is you convert this into the monotonic sequence that you want. So here's kind of the big hammer that we're going to use. This lemma is the hard part of the proof, which is why I'm sort of cheating by saying this is the proof. Proving this lemma is the hard part of the proof. We've already seen a version of this lemma, right? The thing that we proved before, the really easy thing that we proved before, that was a single 3, 2 move followed by 0, 2, 3 moves, right? So that's like this, right? You've got a single 3, 2 move followed by 0, 2, 3 moves. And we've already seen that you can replace this with a 2, 3 move followed by a 2, 0 move, right? We just saw this a couple of slides ago, right? And what I'm saying is you can actually prove something much more general, which is if you have a single 3, 2 move followed by any number of 2, 3 moves, right? So this could be 1, 2, 3 move, or 2 or 3, or however many you want. Then you can replace that by a sequence of 2, 3 moves followed by some sequence of 2, 0 moves. So what that replacement looks like is you get that, right? So maybe I flashed through that too quickly. So let's go back. So you have this 3, 2 move followed by 2, 3 moves. You delete that sequence and you replace that with a possibly much longer sequence of 2, 3 moves followed by 2, 0 moves. And the point is, the invariant, when you sort of keep applying this lemma, is at the end of your sequence, what you have is what you want, right? So like let's go back again. Okay, so at the end of your sequence looks the way you want it to look like, right? But what you've got sort of beforehand is some junk. Like in particular, you have some 3, 2 moves that you don't want. And so every time you see one of these 3, 2 moves, you look at all the 2, 3 moves that follow it and you replace that sequence like this. And again, what you have is the end of your sequence looks the way you want it to look, and you've got some junk that's happening beforehand, but you can replace that because of the lemma. So I replace this section like so. And like once you've gotten rid of, like the point is once you've gotten rid of all the 3, 2 moves, all you're left with has to be the monotonic sequence that you're after. So I guess the point of this proof idea is really that the proof of the theorem boils down to proving this replacement operation, proving that this replacement operation always works. And that's whatever I have left, let's say 10, 15 minutes to talk about this replacement operation. So here's the replacement operation again. This is what we need to prove. Yeah, and this is where things sort of get a little bit hairy. So let's see how we go. I want to draw triangulations because, like, even with the proof from a few slides ago, it was like a little bit tricky to visualize what was going on. Like, it's possible to visualize what's going on with triangulations, but it was a bit tricky. So I claim that once you get familiar with these things that I call that is called special spines, it's kind of easier to visualize things in that setting. But I think a lot of people that I talk to like aren't convinced by this. So we'll see how we go. And so here's how you convert a triangulation into a special spine. So here's just like a model of two tetrahedra that are glued together. And the idea is you replace each tetrahedron with this thing, right? Which Matveyev calls a butterfly. And he sort of remarks that it's a very strange butterfly because it has 6 wings. So it's not really a butterfly. But anyway, Matveyev calls it a butterfly. So what's happening here is you've got this kind of vertex in the middle with 4 edges coming out. And what that corresponds to is the fact that the tetrahedron has 4 triangular faces, right? So sort of that's dual to a vertex with 4 edges coming out. And the 6 edges of your tetrahedron correspond to these sort of faces or wings of the butterfly. That's kind of what's going on here. And the point is, if I insert one of these butterflies into each tetrahedron, the gluings of the tetrahedra tell me how to glue these butterflies together. Yeah. Because the fact that this triangle is glued to, like, the fact that this triangle of this is glued like that tells me that I should glue these 3 pieces of the butterfly together in that way. Like, if I were to rotate them, then you also correspondingly rotate the butterflies, right? And so you can get this dual picture where you'll notice that this spine fits a two-dimensional picture, which, I don't know, it's sort of easy to draw, right? Because you can embed this two-dimensional thing, sort of, you can draw it in 3-dimensional space, and somehow it's easier to visualize in some way. I've already talked about some of this, which is how the duality sort of works. So like, you've got these vertices, like the points in your spine, as I say, come in 3 types. So you've got these vertices, and they're all sort of isolated from each other. So you've got like, they're discrete. You've got a vertex here and a vertex there. And as I said, each vertex is sort of corresponds to a tetrahedron. You've got kind of edges where the neighborhood looks like you've got 3 kind of pieces coming in. So these correspond to your edges, right? So like every time you've got an edge going out, you've got 3 sort of faces emanating out from that edge. And the point is that's dual to a triangular face, as I said. So like, for example, like if you look in this picture at the top, which is maybe a bit small, like you've got these 2 vertices that are connected by this edge, right? That exactly is dual to the fact that these 2 tetrahedra are glued along that triangular face. And then finally, you've got these points that just look like you're part of a surface, right? So it's just a non-singular point. And these are dual to the edges of your triangulation. Why is that? Because, like, for example, you look at this edge at the front, right? You've got somehow you've got this sort of wing that touches that edge, and this wing that touches that edge. And if you sort of walked around that edge, if you sort of have that edge here, and you sort of walk around, you sort of walk through a sequence of tetrahedra, right? And as you walk through that sequence of tetrahedra, each tetrahedra kind of gives you like a wing of your butterflies as you walk around. And all those wings stick together to form like a 2-cell. And that's dual to your edge. And so the point is, what I'm trying to convince you of here is that, well, I've told you how to convert a triangulation into a special spine. And the point is, because you've got this duality, if I give you a special spine, you can convert it back into a triangulation. So really they contain the exact same information. So you can flip back and forth between these two settings. And the claim is the special spine setting is often quite good for these things. In fact, maybe it's worth remarking, Matveyev and Pigolini, when they proved their theorem, they didn't prove it in terms of triangulations. They proved it in terms of special spines. So I don't know. It's not just, maybe I say that because it's not just me that finds special spines to be a good setting to do these kinds of things. Oh, right, sure. I should say we're talking about one vertex triangulations. So, okay, so what am I saying here? The complement is a 3-ball. So imagine I delete the spine triangulation. Then you're sort of left with these regions that are kind of a neighborhood of this vertex, and a neighborhood of that vertex, and a neighborhood of this vertex, right? Like what you're left with is a neighborhood of all the vertices. But if you've only got one vertex, then when you delete the spine, all you're left with is a 3-ball. Yeah. So what I'm saying is a spine that's dual to a one vertex triangulation, what that means is the complement of that spine topologically is a 3-ball. Okay. Right. So the point is, how am I going for time now? Okay. The point is you can, right, because you've got this duality, all the moves that I told you about can be expressed in the spine setting. So here's what a 2-3 move looks like in the spine setting. One way to draw it. Up to isotopy, this is one way to draw it. And it's sort of, the way I've drawn this is possibly not the best way to see that these two things are equivalent. The way I've drawn it is more, this is kind of the most useful way to visualize it. Maybe I'll just kind of convince you that combinatorially the right thing happens. So what you've got here, right, is you've got two tetrahedra joined by, glued together along a triangle. So that corresponds to the fact that you've got these two vertices that are joined by the edge E. Yes. And what you want in the new situation is 3 tetrahedra that are glued around an edge, right? So remember, an edge in the triangulation is dual to a 2-cell. And if this edge meets 3 tetrahedra, then the dual 2-cell should meet 3 vertices of your spine. So that's exactly where this, like you've got this 2-cell here that meets 3 vertices, which is new, right? This 2-cell here wasn't there before, just as this edge wasn't there before. Yeah, so sort of combinatorially, at least, right, the right thing is happening here. But the point is you can visualize this as sort of, you take this blue sheet and you slide it along. And this is useful because you can then start talking about, or start visualizing long sequences of moves. Whereas here, like, okay, visualizing a long sequence of moves is a bit tricky. But here, you can get a long sequence of it just by kind of sliding a sheet here, and then you slide along over there, and you slide it along over here, and you've got some long sequence of moves, which is useful. Anyway, so that's the picture of a 2-3 move. So let me show you how the replacement operation works for a more specific example than what I showed before. So before we did a 3-2 move followed by no 2-3 moves. So let's just add 1-2-3 move there and try to see what happens. So what this looks like is you do this 2-3-2 move, which is like an inverse. It's an inverse of a 2-3 move, right? So you undo this 2-3 move, and then you do this 2-3 move here. And we want to realize this by a monotonic sequence in the way that I defined before. So the first step is you're not allowed to use this 3-2 move here, right? You're not allowed any 3-2 moves. So like we have to use 2-3 moves only. So here's what we're going to do. I do a 2-3 move there. And it's like, maybe like, why do you do that? And the reason is, and this is maybe a little tricky to visualize. So when I do this 2-3 move there, I get this vertex here. So like when I do that, I've got this bulge, right? And like kind of on either side of this bulge, I've got these 2 adjacent vertices now. So I can do a 2-3 move on these two vertices. Okay, so this is sort of like you take the two sides of your bulge and you push one side until it kind of slides up onto the other side. Okay, so let me show you the picture of this. Yeah? So you kind of slide it up and you isotope it a bit. And what you end up with is this thing that Matt Vave and others call an arch with membrane, but I'm just going to call it an arch. It's a thing that kind of, it's like a tube and a membrane. It sort of looks like an arch, so we just call it an arch. And anyway, the idea is what this picture looks like is it's sort of this picture, but with an arch. Yeah. So with only 2-3 moves, you can sort of get to this picture, except with the side effect that you've created an arch. And this is kind of the idea: is to do your replacement operation, you just kind of do all of these moves, but you sort of have to carry this arch around with you everywhere. And at the end, you've done a whole bunch of 2-3 moves, and you've sort of got what you want, except you've got this extra arch that you've been carrying around. And then you have to get rid of the arch. And it turns out that to get rid of the arch, well, so this is how this all started, is I was hoping that you'd be able to get rid of the arch using like 3-2 moves. And so the way this result falls out, or also my theorem falls out, is you can get rid of the arch using 2-0 moves. So that's kind of the idea. So do I have time to flick through more pictures? Yes.
You can go for a few more minutes if you want.
Yeah. Okay. So let's flick through some more pictures. So that's the idea, right? So we're carrying around this arch, but other than that, we're just kind of doing all the moves that we wanted to do anyway, and then we have to remove the arch at the end. Okay. So first of all, what I'm going to do, so these pictures are really annoying to draw, so I'm just going to, all the blue faces that are sort of pointing upwards, I'm just going to omit them, right? And everything still sort of makes sense in the sense that you can reconstruct the correct picture. So I'm just going to draw everything like this. So here's our step. We've replaced this 3-2 move gamma with a bunch of 2-3 moves, but we have this new arch now that we have to carry around. And so what does this carrying around the arch look like? So now you've got this 2-3 move delta that you want to do. Now, here's where you run into a problem, right? Because if your arch is there, it's in the way. Yeah, you want to do this 2-3 move between this vertex and this vertex, but there's an arch that's there, and you can't. It's in the way. But I mean, who cares, right? You do a 2-3 move to move the arch out of the way, and then you can do your 2-3 move that you wanted. And maybe it's not so hard to believe that you can always do this 2-3 move. Like if the arch is in the way, you just do as many 2-3 moves as you need to move it out of the way. And then you can just do your 2-3 move as you wanted to before. The idea of what I mean when I say carrying around the arch is you just, whenever you need to, you can just do extra 2-3 moves to move it out of the way. And you'll still have this arch there. And then, as I said, the very final step is you remove the arch. Actually, you have to do some 2-3 moves to kind of set it up so that the arch can be removed. But once you do that, you can then remove the arch using 2-0 moves alone. Okay, so right, so I haven't showed you what a 2-0 move looks like. So here's the picture. Your 2-0 move, what you have is you have, okay, so combinatorially you have two tetrahedra and they become nothing. And this edge that meets two tetrahedra disappears. So combinatorially what you've got here is you've got these two vertices that disappear, right? Like in this picture on the left, those two vertices aren't there anymore. So that corresponds to your two tetrahedra that go away. And you've also got this 2 cell that meets these two vertices. That corresponds to this edge that disappears, right? When you sort of do that sliding, you slide that face out, this 2 cell disappears. So it sort of looks like a a souped up 2-3 or 3-2 move. Okay, again, I'm going to simplify the picture by in the way that I did before. And then this is actually the last slide. So I actually got through everything, which is, I'm very impressed with myself. So this is how you do the removal. And I didn't bother to animate this, which maybe is disappointing to people who were enjoying the animations. So how does this work? You do like a whole bunch of 2-3 moves. Basically, you've got this. Okay. This is kind of hard to explain. So maybe, okay, so you've got this kind of cell here. Okay, so you've got these two vertices, right? You can do a 2-3 move there, which one way to think of that is you take the green face at the bottom and you slide that along until it crosses over that loop, right? And that up to isotopy is equivalent to doing this. Yeah. And you just keep sliding these green faces, those green faces that are pointing downwards, you keep sliding them along until all of them cross over the loop. And then the point is this starts looking like 2-0 moves, right? This, you've got this 2 cell that meets 2 vertices, you do a 2-0 move there, right? And that kind of sort of pulls this loop back. And you repeat this, right? You keep pulling this loop back until you get to this configuration. And now in this configuration, you've got another 2 cell that meets 2 vertices. So you can again do a 2-0 move, which is sort of like, so remember when we built the arch, we sort of had 2 sides that we push together and you push one side up the other side. So now we push it back down and that gets rid of the arch. And that's it, right? Because we sort of before we built the arch and carried it around and we got to the configuration that we wanted, except we had this extra arch and now we've removed the arch. And so what we've got in the end is the triangulation that we wanted to end up with, because, as I say, because we had this extra arch that we were carrying around, but now we've successfully destroyed the arch. And so what we've got left is exactly the triangulation or the special spine that we were after. And that's it. So thanks for listening.
Thanks for the talk, James. Oh, Alex. Does anyone have any questions for Alex?
I have maybe a quick question.
Yeah.
Thanks for the talk, which was, so we have these sequences of like ascending via 2-3 moves and then descending via 2-0 moves. Are you expecting that to be unique, or are there possibly like multiple different ways that you can have a sequence?
Oh, there should be many ways to do this.
Yeah.
There should be many. Yeah. I mean, these sequences are never unique. Or you can always, well, okay, so you can always, there are probably silly things you can do as well, where you do like a completely unnecessary 2-3 move and then just do some stuff to get rid of it later. So, oh, right, you can do a 2-3 move, and then instead of doing it, and you can always undo that 2-3 move using the inverse 3-2 move. But instead of doing the inverse 3-2 move, you do what we did before. You replace the 2-3 followed by a 2-0. So you can just do absolute junk things to get a
if you kind of ignored those kind of like dumb things to do, I guess you would still expect there to be multiple ways.
Oh yeah,
multiple
there would
paths.
still
be. Yeah. Okay, no, that's cool. Thank you.
Well, and all this is speaking to the fact that, as I said, the graph is really well connected. You just can't prove it.
Yeah, it sounds cool.
I wasn't clear on why you specifically want like a monotonically increasing sequence of moves than a monotonically decreasing sequence. Like, why is that interesting, or why is that helpful to you?
I mean, it's partly just because, okay, so the way this started, actually we were hoping that it would be practically useful. Like, Because at the moment, the way you walk through the pachnograph is you're sort of just walking blind. You just try sequences of moves and hope that something works. And whereas if you know that there's some structure that you can always guarantee exists, then maybe you can kind of narrow down your search to specifically look for that structure. Maybe that's more efficient. And that's how this started. It sort of turns out that we don't have great heuristics for actually searching for monotonic sequences. So far, this hasn't sort of turned into a practically useful thing. The other thing is just, I mean, it's, as I said, we don't know much at all. And so anything that somehow, like, anything that you can say about it is somehow good. Like, it's kind of like that degree one edge thing that Henry Seligman did. And it's like, in some respects, that's not the ultimate goal. But if you can, just doing something is maybe instructive for how you might be able to soup up the argument to do stronger things. So that's another motivation that I didn't talk about.
Hi, Alex. Can you do a version of this for ideal triangulations?
Yes, I think so. Yeah, in the paper, which is on the archive, but I don't actually use Matveyev and Piccolini's result. I use Amendola's more general result that includes ideal triangulations, and the exact same argument follows through. So yes.
Right.
This might be a long shot, but I'll just ask broadly, do you know if these kind of things have any relation with modular and Teichmuller spaces of hyperbolic free manifolds? Just because I noted in dimension 2 there is stuff that can be said, but I mean, I don't know if that's a thing for dimension 3 or if you've heard of anything like that.
Yeah, I haven't thought about it. I mean, it would be interesting to think about, but yeah, it's not something that.
Yeah, no, but I was just wondering if it ever came up anywhere or anything. Cool, thanks.
I mean, it's part of the problem is I sort of really don't know anything about Teichmuller space, so it's kind of.
Yeah, all good. I was just wondering, like I thought, because it just seems so similar to some other lower dimensional stuff, but yeah, who knows.
Alex, going back to your the intuition given for the conjecture that you mentioned, you mentioned that the sort of the reason here the intuition why this might be true is that you sort of take two sort of triangulation, you sort of grow them up by 2-3 moves, and then hopefully somehow something happens there. Is there sort of like a reason why there wouldn't be sort of like a local minimum bridge that joins the two graphs together, but otherwise will be unconnected?
No, I mean, like, that's possible, right? Which is why it's not a proof. But,
okay. So okay.
But that would be so bloody weird, because one of the reasons it would be weird is because okay, so one way to say it is like, this is true for subdivisions, right? If you do subdivisions, you know that you always get a common subdivision. Okay, maybe that's not convincing, but that's one. I mean, as your triangulations get larger and larger, you sort of have more and more kind of options for like 2-3 moves to do, and like it would just be so weird that like this kind of exponentially increasing, these two exponentially increasing trees, if they never met. I mean, sure, it's possible that they never meet, and there's some, as you say, there could be a local minimum bridge, but I guess another thing is like if our sort of well-connectedness, if our intuition about well-connectedness really is true, then this shouldn't happen as well. But which is sort of like, if you can prove this, then this is really saying that maybe our intuition is in the right direction. But yeah, you're right. Like maybe our intuition is all wrong. So yeah, you're welcome to be skeptical. because lots of people have tried to prove this and no one's done it, right? So like maybe that's a reason to be skeptical.
Thanks.
What do you mean exactly by well connected?
It's not well defined. It's just, I want to say like, it's not just like for a graph to be connected, it just means there exists between any two vertices, there exists some path. And maybe what I'm saying is I want there to be lots and lots of paths, or maybe lots and lots of short paths, or things that would be useful for computation. Because if you're trying to walk through the Packner graph to simplify a triangulation, it'd be good if there were short paths, and it would be good if there were lots of options or good options to, well, particularly I guess short paths would be really good, but yeah, paths with structure would be useful, because then you can, as I say, you can look, instead of sort of blindly walking through the Packner graph, you look specifically for some particular structure that which could narrow down your search. That sort of thing could be really useful.
Is the Packner graph ever a tree?
Probably not, because you can. I'm pretty sure you could construct sequences that are a loop pretty easily.
That's probably a naive question. So if it's,
I mean, okay, so I don't have
not the case, then
I don't have an answer off the top of my
it's
head,
probably,
but like I'm sure if you just sat down for a while, you could just come up. Oh, is that? Oh, I don't know. I feel like you could find a loop in the in the Packner graph. You could just I at least off the top of my head, I can't think that there would be any. There's no obvious degenerate cases that pop up in my head, so probably.
Does one ever study like automorphisms of this graph? And can that be useful for understanding questions?
I don't think anyone's done it, but it probably. This kind of comes down to the fact that we really don't know a whole lot about the graph.
Yeah.
So there's something that Ben Burton asked me to look at some time ago, and it sort of didn't really go anywhere. But you can do things like associate matrices to a graph, like simple example, like the adjacency matrix or something, right? And so you can then start talking about spectral theory of those matrices, and it like that tells you about connectivity properties of the graph. So like maybe you could start taking like finite truncations of the Packner graph and try to understand the spectral theory of that. But like no one's done it, and like that hasn't gone anywhere. But even that, like we don't know anything about that. I mean, I could go on and on. Like there's just lots of things we don't know, but we would like to know. Automorphism of the graph. No, actually, no one suggested that to me before. So that's I hadn't thought of that.
Do you have any bounds on like how high you need to go up before you need to start looking down, or should start looking down?
That's a great question. So you'll notice in the proof, I have to do a lot more moves than.
Yeah.
So there's an obvious bound that we can do, which is I use Miatovich's bound, right? And then understand how much my sequences blow up that. So it's going to be worse than Miatovich's bounds. But of course, like probably that's not an optimal bound, but that's the best I can give you at this point. Like I don't have a better way of finding bounds other than piggybacking off Miatovich.
Did Miatovich prove his result using spines as well?
That's a great question, because I haven't I haven't read Mianovich. No, I think Mianovich actually works in triangulations, which is a bit nuts. Okay, so he's got 4 papers that do this for different classes of 3 manifolds, which is why I don't say all 3 manifolds, because he doesn't. I don't think he gets all of them, but he the easiest one is he just does the 3 sphere, and that one he definitely just looks at triangulations, and he uses things like he uses normal surface theory, because normal surfaces tell us a lot about 3 spheres, basically. But yeah, I think Mianovich actually works in the triangulation setting. Or at least one of his 4 papers works in the triangulation setting. I mean, this is dual, right? You can convert all of these arguments if you wanted to. But...
Yeah. But I wonder if it's like, you say it's easier to work with spines, so therefore maybe he tried doing it with spines, or maybe these kind of results don't lend themselves to spines. But
I think what Mianovich does is he does something with the 3 spheres. He cuts the triangulation open along normal spheres, and he ends up with bounded triangulations, and he does things with like shellings and stuff, which sort of doesn't translate well to spines. Well,